Okay, so welcome to our wintry day here. Have several things I want to go over. I've had a lot of questions from students. Some of them are from the exams from this semester, but then some of them come from previous semester's exams. And let me just remind you that while I said that I pull questions from the 4 exams, let me remind you of what that means. That means that I take questions from the exams that we've had, but then I change them. And in some cases, a few cases, I only change the numbers. So you really just have to know how to work those problems. But in most cases, I change the problems more substantially. What I mean when I say that I pull questions from the old exams is that you should focus on the content that is covered in those 4 exams from this semester. That if there's a topic that is not covered in those 4 exams, and there are some, then you're not going to see that on the final. But the topics that are covered on the 4 exams are on the final. And many of the questions you'll recognize in some way. You'll say, oh, I see how that's similar question, but it will be asking a different thing. So just be aware of that as you're studying. That it might be useful for you to go back and look at your notes, look at the concept test, look at the problems that we worked in class, or look at the other old exams. So let's start with exam 1 from fall 17. Somebody asked about question number 3 on here. Which of these equations is dimensionally correct? So on these, you put in the dimensions or the units for each of the variables and then check, are they consistent on each side of the equation? So for example, this first one, I have meters, and then I have v squared, that's going to be second squared over meters squared. V is meters per second, it's in the denominator, so I bring it up into the numerator and I flip it over. And then that's equal to meters second squared over meters. That's acceleration, but I've inverted it. So here, this gets rid of here, no, it's from there. These are not dimensionally correct, so 1 is not an option, because the units have second squared over meters over here, and only second squared on the right-hand side, so not dimensionally correct. Now, let's look at the next one. I have a kilogram meters squared per second squared. That's this first one. Is equal to, actually, you know what? Let's simplify this a little bit. I'm going to get rid of the meters, because notice that I can get rid of it all the way throughout. So I'm just going to lose that kilograms, because I can divide through by m on each side. So anyway, then I have meters per second squared. That's x times a. So far we're okay, meters squared per second squared. And then in this last part, notice the half, that doesn't have any units, and so this is meters squared per second squared. Ding, 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 that one is okay, because I have meters squared per second squared here, here, and here. Okay, so that one's okay. Let's look at the other one. I have meters right here, meters per second, seconds. Okay, we're okay so far. Let's look at this. I'm going to get rid of these x's because they just cancel out. And so then I have meters squared per second squared, and then second squared over meters. That's acceleration, but the inverse. That cancels with one of those. Look, we're okay with that. So I have 2 and 3 are both okay. Okay, so that's exam 1 from fall 17, number 3. Let's look at exam 2 from fall 17, questions 1 through 3. This was a sequence of questions about projectile motion. So I have a ball that's thrown in the air at an angle of 30 degrees to the ground with an initial speed of 40 meters per second. How long does it take to reach its maximum height? I always love to draw a picture. It just helps me to think about the question and what's going on. And this is our typical projectile motion question. And at this one, I'm asking for what is the time when it reaches the maximum height. What do I know about that position? Well, I know that Vy is equal to 0 at the top. So I can figure out, since I know this information about the velocity in the y direction at the top of the trajectory, I can say, well, Vy at the top is equal to V naught y, that's the y component of that initial velocity, plus Ay, that's the acceleration in the y direction, times t top. And so I say 0 equals 40 times sine of 30 and sine of 30 is a half. So I'm going to go and say 40 times sine of 30 is equal to 20. I said 40 times sine of 30, that gives me the y component of the velocity, minus 10 meters per second squared times t top. And I solved that for t top. It's negative 20 divided by negative 10, so t top is equal to 2 seconds. And that's the answer. It takes 2 seconds to get from here over to here. What is the horizontal range? Well, I have to do a couple of things. First, I have to recognize that t total is twice this time, because whatever time it takes to get here is symmetrical. It takes the same amount of time to get here. So the t total is 4 seconds. Then I need to figure out what is the velocity in the x direction. And notice that this is also going to be equal to the initial velocity in the x direction, because there is no acceleration in the x direction. There is never any acceleration in the x direction as it goes through this trajectory. So that's going to be 40 meters per second. Sorry about that. 40 meters per second times cosine of the angle. Was the angle 30 degrees, and that's equal to 35 meters per second. So now I got Vx, I got t, I know there's no acceleration, so x is just equal to Vx times t. That's 35 meters per second times 4 seconds. That's 140 meters. What is the x component of the initial velocity? Well, you already found this. It's 35 meters per second. We had to find it up here. So that's a good sequence of questions. You'll certainly see some projectile motion, and it could be similar to that. Exam 3 from fall 17. Somebody asked, whoops, exam number 3, number 2. Ah, yes, this one. So, how fast is the kid going when he reaches the bottom? Well, let's do it 2 ways. Or let's do it first without friction. Got this 10-kilogram kid over here. He has potential energy. Down here, he only has kinetic energy. If there was no friction, all of that potential energy would transfer into kinetic energy. If there is no friction. But it turns out the friction does work on the kit. But first, let's solve this for the, if there was no friction. It would be mgh equals 1/2 mv squared. The masses cancel. Actually, yeah, masses cancel. And then that's going to be 10 meters per second squared times the height. It's 2 meters high. Equals 1/2 v squared. That's 20, 40, square root of 40. If there was no friction, the speed would be 6.3 meters per second. If there was no friction. So I can go and get rid of that one because I know there is friction. And you know what? I'm going to get rid of both of these and just tell you right off of their hand that the answer is A. Because I know if there's friction, he's got to be going slower. But let's just go ahead and verify that that's true. I love being able to work problems and get rid of options. And that's a good skill for you to have when you're taking these standardized tests, is to be able to read a problem and just intuit which answers are wrong. So now, he has a certain amount of potential energy at the top. When he gets to the bottom, as he goes down the slide, the frictional force does work on this kid. That deducts from that potential energy. When he gets to the bottom, he has less kinetic energy than he started with in potential energy. So, mgh minus the frictional force times the distance is equal to 1/2 mv squared. Now, our masses don't cancel out here, but we got the mass anyway, so it doesn't matter. 10 kilograms, 10 meters per second squared. H is still 2 meters, minus the frictional force is 5 newtons, times 4 meters. That's the distance over which this frictional force occurs. And if it occurs over a longer distance, then guess what? It does more work. And that's equal to 1/2 m, 10 kilograms times v squared. That's a 200, that's 180 times 2 divided by 10. Square root of all that is equal to v, and that's equal to 6 meters per second. So that's the answer as we knew it would be, but still it's good to go through and verify that. Let's look at 26 also on this question. I think it was about rotation. Ah, yes. So the fan is spinning as shown, and it's speeding up. First of all, let's recognize that omega is clockwise, and so it's in the negative direction. Remember, clockwise is negative, counterclockwise is positive, and that has to do with our right-hand rule, but we're just taking clockwise as negative. So our omega is in the negative direction. So I can get rid of this and this. Now I want to recognize that this thing is speeding up. So alpha, the acceleration, is opposite direction of omega. So whereas this was negative, alpha is going to be positive. I'm sorry, never mind. No, that's not correct. It's speeding up, so alpha is the same direction as omega. I know that everybody was yelling at the TV in that because that was a bad call. Right, so alpha is the same direction as omega. So since omega is negative, alpha is also negative. Negative acceleration does not necessarily mean slowing down. Negative acceleration means an acceleration in the negative direction. And if your velocity is also in the negative direction, then your object is going to be speeding up. Okay, so that's 26. Now we're going to look at some old exams. We'll start with Fall 12, Exam 1. Number 19 and 23. Okay, yeah, you had these on your other exams, so these are not inappropriate. Number 19, here you're translating a position versus time graph to a velocity versus time graph. Think about what your velocity does. Here, I have a negative, big velocity. So it's both negative in the negative direction, because the slope here is negative, and it's big. And over here, I still got a negative velocity, but it's small. So if I were to think about my velocity versus time graph, first of all, it's only going to be down here in the negative portion, in that fourth quadrant, and it's going to go from being big negative to small negative. So big negative, small negative. So my answer should look something like this, and that's D. Number 23, that was 19, 23. Okay, I throw a ball up in the air. It goes up, comes down, and I catch it. Now remember, we worked a problem before, but up here, I'm looking at the velocity. The velocity is equal to 0 here. That the object goes up, stops, turns around, and comes back down. So I can get rid of some things. I can get rid of this one, because not 0 here. I can also get rid of this one, not 0 at the midpoint, where it should be. So it's either A or C. And if you remember the experiment that we did in class in the lab, you know that C is for a bounce pass, and that's not what this is. So let's look here. I have a big positive velocity because it's going up, and then over here I have a big negative velocity. Big positive velocity, big negative velocity, 0 velocity. Connect the dots. Notice too that the slope of this is always negative. It has a negative slope, and in fact that negative slope is negative 10 meters per second squared, which is equal to our acceleration due to gravity. So that was 23. Let's look at Fall 13. Exam 2, or Quiz 2 as I used to call them, number 12. I don't reuse test questions, so don't expect to find the same questions, but sometimes you'll see similar questions. Let's see, two forces act on a 6 kilogram object. Whoops. One is 10, and the object accelerates at 2 meters per second squared. What is the greatest possible magnitude of the other force? We had a similar question, or I think there was one that had to do with frictional forces. What was the frictional force on the object in exam 2 from fall 17? This is a similar question, except we're just not calling it friction. So here I have a 6 kilogram object. One force is 10 newtons. I don't really know the direction of it, but I'm just going to draw it in this direction, and we'll see what happens. And the object accelerates at 2 meters per second squared. Now, I don't know the direction of my acceleration. That's where this gets a little tricky. But I do know that the net force on this object is equal to mass times acceleration. My mass is 6 kilograms. My acceleration is 2 meters per second squared, so my net force on this is 12 newtons. And so the greatest possible magnitude, there are actually two possible answers, that I could either have a force of 2 newtons in this direction, that would give me a net force of 12 newtons, or could get rid of that and put in 22 newtons of force in that direction, and that would also give me a net force of 12 newtons. And since I'm looking for the greatest possible magnitude of the other force, the answer is going to be B. Ooh, that's a good question. So what is this, quiz 2? Fall 13. Okay, that's it on that one. Okay, now next, fall 15, exam 2, number 12. $80-kilogram person falls out of an airplane and eventually reaches their terminal velocity. Then we estimate the force of air friction at this speed to be what? Well, if they reach their terminal velocity, what that means is their maximum speed, that they come to some speed where they're no longer speeding up. That means that the acceleration is equal to 0. And if the acceleration is equal to 0, that means that the net force, or the sum of all the forces, is equal to 0. So if you got this person that is falling, they have a force weight, and then they also have the force due to air resistance. And so the force due to air friction or air resistance is going to be equal to the weight. And the weight is equal to mass times the acceleration due to gravity, which is 800 newtons. So that's the answer for number 12, is 800 newtons. See, that's fall 15, fall 16, number 17 from exam 3. Between 0 and 30 seconds, the second hand of an analog clock has what speed? Well, think about your clock. This is 0 seconds. This is 30 seconds. It covers an angle of 90 degrees, excuse me, not 90 degrees, 180 degrees. Think about your unit circle. I have 0, pi over 2, pi radians. 180 degrees is equal to pi radians. And so I cover an angular displacement of pi radians in 30 seconds. So pi radians over 30 seconds. I'm just doing delta theta over delta t. That is going to be my angular speed, omega. That's 3.14 over 30. It's going to be about 0.1. So 17 is A. That was fall 16. Well, let's look at fall 17, exam 4, number 18. Was that this one? Yes. Okay, so the manometer. Actually, this problem, I say I don't reuse questions, but this problem actually was from a previous exam. I think it was the only one on this test. The problem with this one, the difficulty that students face, is there's more than they really need. I don't really need the temperature. I don't need the diameter of the tube. All I really need is this and this and this. So I want to know the pressure of the methane. I want to know what this is equal to. I know that my P naught over here is 1 atmosphere, and that's equal to 1 times 10 to the 5th pascals. And I know that my H is equal to 5 centimeters. Of course, I'll need to convert that to SI units, or 0.05 meters. I'll move that decimal place over 2 places to 0.05 meters. So my pressure is equal to P naught plus or minus rho GH. Remember, because the rho GH, that represents the pressure of some column of fluid that sits above a certain point, and I'm trying to figure out what is the pressure right here due to this column of mercury. Is P bigger or smaller than P naught? Well, because of the relative heights of these two, P, it just ain't big enough to overwhelm P naught. So P is less than P naught. Well, we can, once we recognize that, we can see the answer is going to be 93,000. Since P is smaller than P naught, and P naught is 100,000, then that has to be the answer. But let's continue. So that's 100,000 pascals minus 13,600 kilograms per cubic meter. You should go onto your sheet and find the table for densities, and you'll see that for mercury. G, of course, is 10, and then H is 0.05. If you do that, you find that it's equal to 93,000 pascals, or newtons per square meter. So D is the right answer. That was the last one that students had written to me. But if you have additional questions, I won't be able to make a video at home, but I can certainly answer any questions that you might have over email, or if you need to call, just shoot me an email and we'll set up a time to talk on the telephone. Or of course, our exam's not till 1 o'clock on Monday, so you can come by Monday morning and I will be in the office from 8 until lunchtime to answer your questions. All right, again, 1 p.m., Pelcha Auditorium. Some of my online students, you'll be coming in at 3 if your schedule doesn't allow at 1. All right, stay warm this weekend.